I see a lot of friendly names and people I've met and people whose papers I've read. So I'm just going to the slides here. This paper is about recovery theory. And there's a curious situation, which is a theoretical problem as well as an empirical one. And that is that when Steve Ross or Peter Carr do recovery theory, they do it in US dollars. And then when Ian Martin in England does recovery theory, he does it in US dollars. And then when Christian Dorion in Canada does it, he does it in dollars, not Canadian dollars, but US dollars. So this is a problem because the predictions of the theory could be different in different numeraire, and the theory has not yet been successfully applied. So the aspiration of the theory is great. It's to recover physical probabilities from risk-neutral probabilities. That is, to look at option prices and somehow figure out what the probabilities are. And it's actually fairly weak in assumptions. It assumes a stationary state space and time-separable preferences. So if you have time-separable preferences, then the stochastic discount factor is the marginal rate of substitution. And the marginal rate of substitution between consumption today and consumption in a future state is just the ratio of marginal utilities. Okay. That sounds good, but for one thing, I said there's a stationary state space, and that's going to depend on the numeraire. Right? Perhaps even worse, this stationary recovery theory can't accommodate the binomial model or the Black-Scholes model. Right? And I'm pretty sure that Steve Ross was familiar with the binomial model. Right? But on an empirical basis, recovery theory relies on interest rate variation. And the only prediction of recovery theory is that the long bond is log efficient. It has the highest mean for the smallest log risk. And that's obviously false because there are a lot of strategies in fixed income alone that outperform the long bond. Right? The long bond earns a very small return premium. So I'm going to fix this situation by generalizing recovery theory a little bit, and I'm going to show you the right numeraire to use for recovery theory. Okay. So instead of assuming a stationary state space, I'm going to assume stationary growth. Right? So if you look at the Mayra-Prescott equity premium paper or the Cox-Ingersoll-Ross paper, they have constant or stationary growth through constant returns to scale production technology. So I can handle power utility, but I can also handle Epstein-Zinn recursive preferences and other preferences. And I actually formulated this long ago and called it path independence. Ross calls it transition independence, but it's the same concept. And it turns out that this will be sufficient to recover physical probabilities from risk-neutral probabilities, and it will restrict the variance premium against the equity premium. In addition, it's going to tell you the log-efficient security. The log-efficient portfolio is not going to be the long-term bond. It's going to be a long-term power security. And this turns out to be equivalent to Ross recovery, but in a numeraire that uses this so-called power security, which pays off some power of the market portfolio. So just to foreshadow the results, suppose you had some ETF, a levered ETF that paid out the market return squared, or the square root of the market return, or the reciprocal of the gross market return, right? You have various powers. Then my theory predicts that one of those power securities would be log efficient. Right. So what we really need is just one good example to figure out what's going on, because I found the original recovery paper very opaque, very difficult to read, because in the exposition, Ross just whipped out this Perron-Frobenius theorem and said, look, there's some special eigenvector of a transition matrix, and I recover everything. But it didn't really explain the intuition of why this was a good idea and what it meant economically. And I'm going to show you, once we see the simple example, everything generalizes. So I have the risk neutral dynamics for the Heston square root model, right? First equation is risk neutral, and in particular we have a square root process. And temporarily, I'm going to assume the same sort of physical dynamics here. The physical dynamics differ from the risk neutral dynamics because there's an equity premium, I call mu for mean, and the parameters of the variance are different, right? These physical parameters will be different from the starred risk neutral parameters. So we have complete markets and only two sources of risk, the DZ1 and DZ2. And the fundamental theorem of asset pricing says that there's got to be some non-negative martingale, or non-negative pricing kernel that makes everything into a martingale. So this is sort of standard asset pricing theory. And we can actually identify this pricing kernel. Because markets are complete, there is a unique pricing kernel, and it has this ugly integral stuff in there. All right, 1 second while I adjust my window. Let's see, having some minor window issues here. There. So here's the pricing kernel. It has the stock price to a power, and it has time. That's not important. It has volatility or variance here. It's exponential affine, and that's good. But it has this very strange integral here, which is path dependence. And this says, I hate that term. It's typographically ugly, but also it says that the pricing kernel, that is the stochastic discount factor, basically depends not only on where you start and where you end, but it depends on how you get there through this integral. And that is the path-dependent term that violates Ross's transition independence condition. And I will declare that it should not be there. I call it path independence. Okay. So, all right, that's what this slide says. Now, I can come up with theoretical reasons why the pricing kernel should be path independent. And I'm going to, I'm not going to be pretentious or anything. I'm going to say, look, you're trusting me to write down equation 1 to describe risk neutral option prices, right? And in equation 1, I said there's a square root process. And usually people don't object. They say, okay, it's your model, you get to pick the process. And I picked a square root process. People don't object to that. Well, I'd also like to say that the pricing kernel is a function of my state space. And if you trust me to pick the state space, then you should trust me to pick the pricing kernel as a function of the state space. Now you could say, wait, so this is a principle of parsimony or practicality. Right? You might say, wait a minute, absence of arbitrage will not guarantee that. It could be that the pricing kernel depends on the integral of the past variance, your square root process. And I'll say, yes, that's true, but there are a lot of state variables that are not in my state space. We could have lags of volatility, and we could have the business cycle index or GDP or consumption and lags of everything. And we could have integrals or stochastic integrals of everything, but those things aren't in my state space. And that's okay. I have, as an economist, I have to pick some variables that I think are relevant and some that are less relevant. And so this is just a parsimonious, pragmatic assumption. So let me just say yes. All right. So the other assumption implicit here is that option prices should be homogeneous in the stock price or the spot price, right? In other words, options should depend on moneyness but if you double the spot price and you double the strike price, you should double plain vanilla option prices. Right? So options and returns in both the physical and the risk neutral measure should not depend on the level of the spot price. And that's why we have that power of the spot price. So if that parameter gamma here is equal to 0, in other words, if the stock price doesn't appear, this is just Ross recovery. It says you have a constant discount rate delta. You have a delta, and you have some arbitrary or general function h of the state space, and my stationary state space is merely a square root process. But this work generalizes to other stationary state prices as long as everything is homogeneous in the stock price. Okay. So now comes the math. I'm going to impose the martingale condition along with the risk neutral process, making no assumptions about the physical process. And instead of using the this function h in the first equation here, instead of using h, excuse my Zoom incompetence here. Instead of using that, I'm going to use the reciprocal of h. So I call that n. Peter Carr called it n also. He said it was n for numeraire, and I said, oops, I just use n because it's the next letter after m. But in any case, it's easier to express the prediction in terms of the reciprocal of the pricing kernel, which is basically a function of the state. And in this case, we get the same PDE as Linetsky and Chin did when they analyzed the square root process. And it's the equation at the bottom of the page. It's an ordinary differential equation. And let's see, excuse me there. I'm having minor hardware issues, but there we are. That is an ordinary differential equation, a second order ordinary differential equation. And Hansen and co-authors call it an eigenfunction equation because it says that some linear operator on n, on the reciprocal pricing kernel, is in a linear equation with n. It's proportional to some multiple of n. So they say that's an eigenfunction. But it's a second order ordinary differential equation, a linear equation, and it does depend on gamma, as well as the discount rate. Well, so here's the recovery theorem or proposition I have for you. Let's assume the risk neutral dynamics, but not the physical dynamics. Then there is a unique path independent pricing kernel, or the reciprocal n, and it has the simple exponential affine form. So if you give me gamma, then there is a unique psi here, and psi satisfies some quadratic equation. So the usual method for solving these ordinary differential equations is to guess the solution, and we can guess that it's exponential affine. And if we just plug things in, and we find that there is a quadratic equation for psi. All other equations are explosive, or all other solutions are explosive, and only one of these quadratic roots gives you mean reverting behavior in the physical measure. So it turns out that if you assume recovery, you get the same pricing kernel I showed you earlier without the integral term. Right? And this is true more generally, that there is a unique pricing kernel in this model that gives you stationary stock returns. Right? So we don't need to assume both the physical and the risk neutral measure. All we need to do is assume the risk neutral measure and assume this recovery form. And recovery theory says that the pricing kernel is homogeneous and that it does not depend on the path of the state space. It depends only on the current state space. Okay. So that is the theory. Let me pause here and see if there's any questions or clarifications needed.
So there aren't any questions in the chat right now, but if anyone has a question, I guess they should feel free to unmute themselves and ask it.
No?
No questions. Okay.
Well, great. So, so you might say, what does all this mean? Right? I've assumed I would argue it's not a weird functional form. I just said that the pricing kernel is a function of the state space times the stock price to a power. And I don't know that power. That power will determine the equity premium. So we already know that if you like the Black-Scholes model, then you know that we can't recover the equity premium from option prices, right? If you use power utility and log normal distributions, Mark Rubenstein showed that you get the Black-Scholes formula. So the Black-Scholes formula cannot tell us what this power is. But if you give me this power, then you can determine the equity premium and, in fact, the entire distribution of stock returns. So I'm assuming sort of a generalization by multiplying the Ross pricing kernel by a power to say that the kernel is homogeneous and path independent. I want to now consider valuing a particular security. Since I have the pricing kernel, I can value calls and puts and anything I want. And I'm going to consider valuing a security that pays off a power of the stock price. That is this, this middle equation here. This says that the terminal payoff is a power of the stock price. Whoops, I'm sorry, not that one. Here we are. The terminal payoff should be a power of the stock price, and there's a standard PDE above that every contingent claim satisfies simply through absence of arbitrage. And the solution, not surprisingly, is a power of the current stock price times some exponential affine solution, which is complicated, but is in the paper. Well, I've solved for this security, and it's interesting. I mean, it'd be kind of cool if the CBOE would trade ETFs that paid off the stock price squared or the square root of the stock price or other powers. But why did I choose this security? And the answer is I want to consider a long-dated power security. So currently I have a terminal date, T, and the functional form depends on the maturity. That is, how far off is the expiration or maturity from today's date. I want to let that go to infinity. And when I do that, it turns out that I recover the parameters of preferences, right? The pricing kernel has an equity risk aversion, this gamma, and it has a variance risk aversion, psi. If I can observe this, the power security with a very long maturity, then I can observe the preference parameters. Oh, I'm sorry, I can observe D if I choose the power security with power minus gamma. So I do have to know gamma, which is effectively the equity premium, but if I know the equity premium, then I can recover the variance premium by looking at the price of a very, very long security that pays off the correct power of the stock price. So that means that the marginal rate of substitution, or the stochastic discount factor, is effectively observable through option prices, right? You can use the VIX methodology to construct a portfolio that pays out any function of the stock price. Right? For example, it could pay off the log of the stock price with a log portfolio, or it could pay off any power of the stock price. So if we have enough options with different strike prices, and they're very long-term options, we can form this portfolio, and the price of this portfolio will let us observe psi, the variance risk aversion. Moreover, see if it has a slide, the reciprocal of the gross return is the stochastic discount factor, M, or the change in M, the ratio of M over time. And if we divide by the reciprocal stochastic discount factor, in other words, multiply by it, we get, and any security return must be a martingale. So this tells us what the right numeraire is in Ross recovery theory. The numeraire is not the US dollar or some other currency. The numeraire is equal to this asset return S raised to a power. And I think of S as the market portfolio in line with, say, Mayra and Prescott's consumption-based asset pricing. But you need to take a stand, of course, on what this portfolio S is. And the S&P 500 seems like a reasonable proxy. And then some power of or some derivative which pays off the power of the return is the appropriate numeraire to use. Okay, and I think that this is a plausible numeraire because since it's long term, it has some interest rate risk in it, and since it well, it obviously depends on variance, so it has a variance premium, and if the returns are stationary, then it just combines all risks so that it's a log efficient portfolio. And from an old literature, we know that the reciprocal of this return makes everything into a martingale. In fact, this is John Long's numeraire portfolio. So all of these closed form solutions and exponential affine solutions are convenient. They obviously depend on the square root process, but this latter result does not. The latter result about the numeraire portfolio is more general, but of course I can't give you closed forms for an arbitrary process. So let me pause here to see if we need any clarification, any questions at this point? No? All right, good. So I'm about halfway through with the slides. I didn't want to rush anyone. I will continue. So I would like to estimate the variance premium. And I should mention that if the equity risk aversion has the right sign, and if variance is negatively correlated with stock returns, which I'll show you from summary statistics is true, then the model predicts a positive equity premium and a negative variance premium. Right? And I'll give you the intuition for that. Variance is a negative beta asset. So even if investors didn't care about variance per se, the fact that variance has a negative beta means that investors would accept a negative return premium for variance risk to hedge them against the positive fluctuations or the negative fluctuations in the market. But there's an additional independent component to variance, and the theory predicts that this independent, or it's not really a delta hedged component, but it's a beta hedge component. This should carry a negative premium as well. So in order to test the model, I need an asset that's very sensitive to equity fluctuations. And this is obviously just the return on the S&P 500. And then I need an asset which is very sensitive to variance fluctuations, and I'm going to choose the VIX. Right? The VIX is an option portfolio, which almost by definition has variance risk. Right? And usually the VIX is interpreted as a variance swap. That's not precisely correct, but it's an excellent approximation. I have actually constructed dynamically hedged returns on the underlying VIX portfolio, and they are 99% correlated with realized variance divided by the VIX price. So it doesn't really matter which way I run it. Therefore, I'm simply going to use the realized variance divided by the VIX squared, which is the price of the VIX portfolio, to calculate returns. But I also have another security I want to use, which is the 3-month VIX. All right. The CBOE publishes both a 1-month VIX and a 3-month VIX, and you can use that to make a term structure bet. In particular, it's really odd that the VIX security involves paying the variance price, right? It involves buying options, which have a U-shaped payoff cumulatively. But the payoff to VIX doesn't depend on options. It just depends on the path of the S&P 500. Well, if you want variance risk, you don't want something that's sensitive to anything involving the S&P 500. You want it to be sensitive to variance. And that is the 3-month VIX. The strategy I'm considering involves buying the 3-month VIX and selling a sequence of 1-month VIXs today, in 1 month, and in 2 months. So if you do that, you make a bet by basically buying realized variance over the next 3 months, and then you successively sell 1-month variance 3 times in a row. This is very much analogous to buying a long-term bond and borrowing at the short-term rate until expiration or maturity. And this actually is an excess return portfolio strategy. This is a feasible dynamic strategy, and it's actually a bi-monthly strategy, because if you buy the 3-month VIX, you sell the 1-month VIX today, you sell the 1-month VIX in 1 month, and you sell the 1-month VIX in 2 months. But at that point, you can liquidate the portfolio, and you're done. So let me show you a picture of volatility. I have both the 1-month volatility and the 1-month VIX and the 3-month VIX. And in the blue line, I have realized variance or realized volatility. And the most obvious thing is that realized volatility, it tends to be lower than risk neutral or option implied volatility. And that is the negative variance premium. This is well known, it's not original, but it's just kind of cool to look at it. But what I want to assert is that if you look at this graph and you have really great vision and you have really great computational skills in your head, you can deduce the equity premium. Right? And if you believe in recovery theory. I think, that's strange. How is it that by looking at a graph of variance, I can figure out the equity premium? And I'll show you. Well, in a couple slides, I'll show you. First, let me talk about summary statistics of VIX. That they basically show what you saw on the graph. We can see that the 3-month VIX is slightly larger than the 1-month VIX here. We can square the VIXs, but that gives us weird units. Notice so that the realized standard deviation is 16%, which is lower than the 19 to 21% risk of the options on average. So that tells you that there's a negative variance premium. And let's see. All right. If you look at the correlations are very strong between changes in variance or changes in volatility and the S&P 500 return. So variance is strongly negatively correlated with the market. It's a negative beta asset, and it has a negative variance premium. I would like to explain that without using that fact as a starting point. So to do that, I want to talk about the expectations hypothesis. So Stein actually wrote a paper where he tried to predict future standard deviation based on current standard deviation. And the analog with options using exact excess returns would be to predict the return on my excess returns on the 3-month VIX. Again, the 3-month VIX is a nice security to use because I'm not actually trading the underlying S&P 500 here. I'm just buying options with 3-month expiration or maturity, and I'm selling a bunch of options with 1-month maturities. So at no time am I actually depending on the actual risk of the S&P 500. I'm just buying options and selling different options. And the expectations hypothesis in this sense says that the expected future variance is equal to the current forward variance. Right? Remember, variance is VIX squared, so this says that the future squared VIX over the next 3 months is equal to 3 times the current 3-month VIX. right? At least an expectation. That is the variance expectations hypothesis, and it's not ad hoc here. It is actually equivalent to the excess return on an option portfolio. So the natural way to nest the expectations hypothesis with an excess return strategy is to do a linear regression. And this is the analog of Stein's linear regression. We regress future variance here in excess of 3 times the 3-month VIX variance on the 3-month VIX variance today. Okay. If you believe the expectations hypothesis, then this beta coefficient should be 0. Beta should be 0. And alpha, we're really uncomfortable with alpha because the expectations hypothesis says it should be 0, but in practice, we run the regression and we kind of ignore intercepts. So what the expectation hypothesis tests is algebraically equivalent to conditional variation in the return premium on long-term options, at least if you set it up accurately this way. So that's the expectations hypothesis, which does not follow from economic theory, or not from absence of arbitrage or any stochastic discount factor. And now I'm going to modify the test by adding in a stochastic discount factor, right? Asset pricing theory says that excess return should basically be a martingale when we multiply by the stochastic discount factor. And so I'm going to also do this regression using the stochastic discount factor, which is just an exponential function of squared VIX, right? So this theory tells us what the stochastic discount factor is, and I'll use it in the test. Okay, the point is to show that recovery theory has bite and can produce accurate predictions about security returns that transcend the expectations hypothesis regressions or explain the violations of the expectations hypothesis. Furthermore, I want to recover stuff, and I have this martingale condition. I have that the covariance of the excess return, on the VIX 3M here with the stochastic discount factor is 0. Okay. Recall that the stochastic discount factor has 2 parameters. It has an equity risk aversion gamma and a variance risk aversion psi. So in order to get them both, I need 2 parameters. So I'll use the VIX, the 3-month VIX, and I'll use the S&P 500. And they actually give me the equity risk aversion 2.5 and the variance risk aversion of 1.6 or negative 1.6. Okay, I don't know what those parameters should be, but they seem small and plausible. That people don't like S&P 500 risk, but they actually do like variance risk in the sense that when there's high variance, people need to be insured, and so they like securities that pay off a high variance and are willing to pay for the privilege of holding those securities. So let me show you, here we have a graph that shows the trade-off between the equity premium, called it mu, and the variance premium, which is the risk-neutral kappa minus the physical kappa. But there's actually a monotonic relationship between them. Right? So the theory doesn't just say that there are 2 parameters. The theory with recovery restricts the relationship between the equity premium and the variance premium. So you can have a big positive equity premium and a big negative variance premium, or with risk neutrality, you can set them both equal to 0 or anything in between. Right? But you can't have an arbitrary equity premium and an arbitrary variance premium because that would require path independence. So if you tell me what the equity premium is, I can tell you what the variance premium is, and vice versa. And in my remaining time, I'm going to show you those predictions. I'm going to test the expectations hypothesis and run the linear regressions with and without a stochastic discount factor to show you that there is predictable variation in the return to variance, that is, in the return on option portfolios. And there's a link between the equity premium and the variance premium. And in fact, these are the same thing. So here is the linear regression. Right? The first column here takes my excess return on long-term options. And this is just based on the 3-month VIX price downloaded from the CBOE. Right? I take end of month VIX prices to calculate excess returns on 3-month VIX, and I do a linear regression on the 3-month VIX at the beginning of the period, and we find a negative coefficient. Right. Stein calls this, I think, overreaction or underreaction. From the standpoint of risk neutrality or the expectations hypothesis, it's a puzzle because this shows that when the VIX is very high, or the 3-month VIX is very high, future returns tend to be low. And when the VIX is very low, future returns tend to be high. Right? This suggests that the VIX is overreacting to expectations about future variance. Right? And it means that future returns can be predicted. When volatility is high, future returns are low. And when volatility is low, in other words, options are cheap, future returns are high.
Actually, can I interrupt for a second? Now that you're
Yes.
getting to the data, there are a couple of questions about the theory. So I think it makes sense to talk to them.
That would be great.
Address them before you get too much into the data. So from Peter Carr,
Yes.
how general is generalizing? Can we go beyond mean reverting diffusion for V under P and allow jumps?
Yes, you can allow jumps and multiple factors. What I want you to do is change the numeraire, and I want you to change the numeraire to a power security. And under this new numeraire, everything should be a martingale, which tells you that this new numeraire is log efficient and is the reciprocal of the stochastic discount factor.
Okay. From John Crosby, Steve, do you assume constant interest rates?
Yes.
Okay. That was an easy answer.
I do. In practice, interest rate variation is a lot smaller than stock return or VIX variation. That's right. I don't think that's really critical. Again, by transferring to the right numeraire, we can make interest rates constant by just using the forward measure. And then we can transform to this new numeraire, which is this power security.
Okay, another one from John Crosby. Alvarez and German 2005 Econometrica say that under weak conditions, the pricing kernel is the product of a martingale and a transitory component, which is the reciprocal of the return on a long-term bond. Can this be reconciled with your CDF based on the power security, with your SDF, excuse me, based on the power security?
Yes, thanks very much, John. That's an excellent question. So, yes, and I would say that Alvarez and German and everyone is doing it in the wrong numeraire. So Ross and Alvarez and German and Hansen and everybody do a decomposition of the stochastic discount factor into this temporary and permanent component, and they find that the long-term bond is log efficient. Right? Basically, all the transitory stuff washes out if you're talking about long-term interest rates, and you're left only with the pricing kernel, the permanent component. So if you transform numeraire to this power security, now the long-term bond is my long-term power security. So I'm saying the same thing in a different numeraire, and I've said that this appropriate numeraire should be a power security. That is, it's a long-term bond in the new numeraire, in the power security numeraire.
Okay.
Does that answer your question, John?
John, if you want to follow up, feel free to unmute yourself.
Let me think about that answer and maybe come back to you.
All right, that's fine.
Okay, and then from Song Byung Seo, do we really need to exclude a pricing kernel with an integrated variance or jump intensity? I'm not sure such setups are truly path dependent. As long as we have the same integrated variance value, it does not matter whether V was small at the beginning of the path or was big at the end of the path. That is, if we choose, if we choose the integrated variance as one of the state variables, it is exactly Markov.
Yes, that's true, and that's a good point. We could put this integral in. We could put in a lot of lagged state variables, right? But if we start putting too many things in, the state variable gets large and unwieldy. And again, this is really a pragmatic choice. So how do I say this? You know, I didn't see it in the slides. I thought it was there. Merton made a bucket shop assumption in his 73 paper. And a lot of people, including me, didn't know what a bucket shop was. But basically, a bucket shop was a fake brokerage before modern regulation where you could buy and sell options on stock prices, but they weren't really connected to the market. They were just making side bets, and they had no effect on the stock price. So Merton basically said that the option depends only on the stock price. And people said, yeah, okay, that sounds reasonable. That the option depends on the stock price, the strike price, and then, you know, maturity and the interest rate. Well, I added stochastic volatility, and I wasn't alone, and said, wait, let's add stochastic volatility and say that the option depends on that. And now the questioner is saying, well, let's add an integral or lags of volatility, and we can do that. Of course, the model gets more complicated. But from a pragmatic perspective, not only do we want parsimony, but we have really low econometric power to estimate means, but we have good power to estimate covariances. So let's suppose that I gave you two candidates for a pricing kernel, right? I say, right, I think the covariance with this thing is equal to the mean. That's my prediction for mean. Well, we can measure variances and covariances exactly in continuous time. And with high frequency data, we're very good at measuring betas and variances. But it's very hard to estimate drifts. So in practice, I can get you a path-dependent variable and a second path-dependent variable, or just a function of my state, and they can locally have identical covariances. So they predict exactly the same risk premium, but they have different means. And we really find it difficult to distinguish these things with a finite sample of data. But we measure their covariance as well.
But
So
Steve, this is Fang.
on.
So the reason why I asked this question was many structural models actually do have this term. For example, time-varying disaster risk models, they have integration of jump intensity. Long-run risk models, they have the integration of stochastic variance. So I was just curious if we define these integrated variables as additional state variables, is it possible for us to apply your recovery theorem to such theoretical frameworks?
Sometimes it is actually. I'm glad you reminded me of this because John Crosby mentioned something about the Alvarez and Germain permanent and temporary components. So these are theoretical questions. Let me bring back my slide. I am screen sharing. And let me go to my pricing kernel just so I can point to the integral part. There. So we see this integral. If we just get rid of the exponential, we're saying the log of the pricing kernel is linear in time. It has this, it's integrated variance and current variance. So what I'm saying is that the pricing kernel is co-integrated with the log stock price. And you would get this from a long-run risk model with Epstein's in preferences. And what I want to do is difference out that non-stationary component. So I allow it, and that's why I have the stock price to a power here. But I'm assuming that the pricing kernel is co-integrated with a log stock price. And then when I switch to the new numeraire, and it's a non-stationary numeraire, I'm going to difference out that component, and I'm going to get back to a stationary state space. So the short answer to Song Young Sio's question is yes, you can accommodate long-run risk and Epstein's-Dinh preferences. And even though those preferences do have some non-stationary component, I believe it differences out after you transform to the correct numeraire.
Thank you.
That is it. Good.
Okay, that's all the outstanding questions. So I should warn you, you have about 10 minutes left, but it looks like you only have
Perfect.
3 slides left, so you're in good shape.
Yes. Okay. So I want to see, am I predicting, there are 2 types of predictions we can have for risk premium. We have cross-sectional predictions and we have longitudinal predictions, right? We have the conditional risk premium and the unconditional risk premium. Excuse me? Someone said that I'm not clear, or maybe I'm breaking.
No, Steve, I think this was just a mic issue on some side. You can go on.
All right, I'm glad it's not yet on my side. Okay, so I want to predict conditional and unconditional risk premia, and the conditional risk premia, that's a regression test. The unconditional risk premia, I can simply pick my I can pick one preference parameter to match the variance premium, or I can predict the other preference parameter to match the S&P 500 premium. And the theory says that there's a restriction between them. I can't arbitrarily pick the equity premium and the variance premium. There has to be a connection. And it's given by this graph. So the first set of predictions is just the expectations hypothesis for conditional risk premia. When you run the expectations hypothesis, there's my red pen, you get a statistically significant overreaction. That is, when VIX is high, returns to volatility or low. When VIX is low, returns to volatility or high. But if I fit the equity premium, and remember, these regressions involve only options. They don't involve stocks at all. But if I use the, if I calibrate the model to fit the equity premium, using the one parameter gamma, then the excess return regression in the expectations hypothesis is no longer significant. The only difference is that I've multiplied the excess returns by the stochastic discount factor. So if I plug in the equity premium, I can fit the expectations hypothesis with no further estimation. Right. No, are there any questions about that? So this theory seems to satisfactorily use the unconditional average equity premium to predict variations in the conditional returns to options. But of course, it's called recovery, and the real promise of Ross recovery theory was that I could recover the entire distribution of stock returns. And at some level, that's going to be impossible because I need to know the gamma parameter. But let's suppose that we try to use bonds to fit the equity premium, or I'm sorry, not bonds, options. And what I've done is I have calibrated my one parameter to fit those expectations regressions. So in panel A shows excess returns. We see that the equity premium is positive at about 0.7% per year. The VIX premium is negative and very large, right? Negative 20, I'm sorry, that's 0.7% per month, right? Roughly 8% per year. The VIX premium is negative 22% per month. And the 3-month VIX premium is even larger. But of course, they're highly levered and highly risky. If I pick this gamma parameter to fit the expectations hypothesis, then I can report the risk-adjusted returns. I want to emphasize that when I fit the expectations hypothesis, I'm fitting conditional variation in returns on options. So I could demean my return series, and I could demean my VIX series, and still run this regression. So I'm not relying on equity returns at all, and I'm not relying on unconditional or averages at all. I can demean all the time series to run the regression and fit my expectations slope. And then I can take that parameter to match the unconditional or average returns on the S&P 500, on short-term VIX, or on long-term VIX. And when I pick that parameter and look at the t-statistics, I'm sorry, I've picked the parameter here to exactly match the equity premium. I apologize, I didn't match the expectations regression, I matched the equity premium, and I find that the means are insignificant. So when I fit the equity premium, I'm able to match both the conditional and the unconditional means of options. So that means that the expectations hypothesis is violated, but the recovery theory is not. Recovery theory successfully predicts both the unconditional and conditional means on options given the unconditional equity premium. And if we want, we can reverse this for a finale, right? I can do what I misspoke earlier. I can demean all the data and I can fit the expectations regression to predict the conditional variation in option returns, right, without using any equity data, only the returns to 3-month VIX, and only the demean returns to 3-month VIX. And when I do that, I calibrate one parameter, this risk aversion parameter, and I predict the equity premium. And when I do that, I predict that the equity premium is 1% per month, with admittedly a large standard error. Okay, and that is really the punchline, that if you generalize recovery theory, you can handle non-stationary prices. And the S&P 500 is definitely a non-stationary price. So you can't apply traditional recovery theory without generalization. But if you generalize it, then you get predictions for the relative risk premia on the S&P 500 and on options, right? Both for the conditional returns and the unconditional returns up to one parameter, which is the equity premium, right? Well, when you run these regressions, it turns out that you cannot reject that the unconditional equity premium matches both conditional and unconditional returns to options. In other words, you do not you reject the expectations hypothesis, but you do not reject recovery theory. Conversely, you can use option returns to back up the equity premium, and you cannot reject that equity premium. It's around 1% per month. Okay, so that's what the final conclusion slide says. I jointly explain equity and variance premia, both conditional and unconditional. And if you really want recovery, then the equity premium is recovered to be around 1% per month.
Great. So actually there's a couple of questions then from Peter Carr. Given the numerical value of gamma, does your theory just recover the P transition PDF of S, or do you get more generally the P transition PDF of S and V?
That's a good question. I'm assuming complete markets, so you get the whole thing. Let me go back to my slide here. So proposition 1 tells you, well, proposition 1 is an old result, just from absence of arbitrage. You get the pricing kernel with this path-dependent kernel that I don't like. But if you assume recovery theory, then this eta parameter is 0, it disappears, and it tells you that the pricing kernel is the stock price to a power times an exponential affine function of variance. Variance is just VIX squared here. And then we can take the physical distribution, which we assume is governed by the square root process. We can take that physical distribution, hit it by this equation. Let me just circle it to make sure it's good. Hit it by this equation, and we get a risk-neutral square root process, and that risk-neutral square root process is in equation 1, or the physical process is in equation 2, and there's actually a transform of parameters from one to the other.
Okay, from Mike Chernoff, what happens if the functional form of the equity premium, that is mu times V, is not known?
Okay, that's an interesting question. And let me think. Well, let's see, we've got mu here. Let me step through this and think about this interesting question. I assume that mu is proportional to V. That's not necessary. In fact, it's not necessary. It comes out of the theory. So I have assumed the risk neutrality or the risk neutral process here. I have not assumed anything about the equity premium per se. That actually comes out of the theory. I have merely assumed the risk neutral process, and I have assumed the recovery homogeneous form. And then the theory predicts that both the variance premium and the equity premium is proportional to the variance. So whether it actually is or not is an interesting empirical question. And right, there's limited power to measure that. But yeah, that's not an assumption. That's actually a conclusion. Excellent question.
Okay, there's also a comment from Oleg Bondarenko, but it's really a comment rather than a question. So I guess I'll let you read it in the chat.
I'll be happy to comment on it if you can read it for us.
So then the comment, existence of an arbitrary positive pricing kernel rules out pure arbitrage opportunities.
Yes.
If the pricing kernel is path independent, then more general statistical arbitrage opportunities also cannot exist. The latter then also induces a new martingale restriction on securities prices, which holds under P and does not involve the pricing kernel, i.e. is model free. Only path independence is required. And then he refers you to his 2003 RFS paper about statistical arbitrage.
Okay,
that was a long comment. I don't know if maybe it's too much for you to address, but anyway.
Well, I won't go into it deeply, especially since I need to review his paper. But the point is that the fundamental theorem of asset pricing says that that you can go from the risk-neutral dynamics to the physical dynamics, or vice versa, with a non-negative pricing kernel, and that prevents absence of local arbitrages. But right, that we get local martingales from that. But there may be more general types of strategies, and the path independence assumption rules them out. So I should definitely be citing that. And Neil, I hope you will make sure I have access to these comments and questions after the seminar.
Dimitri will send you the chat log afterward.
Right.
So you can look at it, so you have his comment.
Okay.
Any other questions? Oh, so there's another question. Okay, which I wasn't looking at while I was looking at you. From Sangbyong Seo again. Isn't the 1% average equity premium per month too high relative to the data?
It is too high, but let's see. We don't have a lot of power to measure means. And the realized equity premium is around 8% per year, I believe. Let me check my summary statistics. I believe I'm still screen sharing. So if we look at the S&P 500, the realized mean is 0.68. I think when I chopped off a couple lags, it went up to 0.7. So the sample mean is 0.7% per month. The standard deviation is 4% per month. And we have 2007 to 2018. So we only have 12 years worth of data here. The standard deviation is not small. So the standard deviation is 4% per month, and we have 16 years of data. Then the standard error is 1% per month. So it's not a bold prediction for me to say that the equity premium is 1% per month with a standard error of 1% per month. In fact, the realized standard error is only 0.7, but we statistically can't reject it. And we know that if we use a longer sample of data going back to 1926 with Wright, Ibbotson, and Singefeld's results, the equity premium is still about 8% per month or per year, which is still about 0.6 or 0.7% per month. So within the tolerance of the data, I've matched it. And I mostly wanted to do that exercise to show you that in practice, you can extract some noisy estimate of the equity premium. So to some extent, I'm fulfilling the promise of recovery theory by recovering the distribution of equity returns from option information. Okay, and I think that's a first.
All right, are there any other questions? If you have a question, you can feel free to unmute yourself rather than type it. Okay, it sounds like there are no other questions.
Okay. Well, Neil, Christian, Dimitri, thank you very much for hosting the entire series. I've seen them and appreciated them. And I'm happy to quarantine as long as I can interact over Zoom and see a lot of good option papers. So I see a lot
I'm really happy to interact with you, Steve. I'm not sure I'm happy about quarantining, but that's we